Welcome to an introduction to subsequence dynamic programming problems. In this video, we'll explore how dynamic programming can be applied to solve a variety of problems that involve subsequences. These are fundamental concepts in algorithm design and optimization. The topics that we will be covering are the longest common subsequence, the longest increasing subsequence, edit distance, and the subset sum problem. Before diving into specific subsequence problems, let's review the fundamental principles of dynamic programming. The key dynamic programming principles are optimal substructure, which means that the optimal solution to a problem can be constructed from the optimal solutions of its subproblems. Overlapping subproblems, meaning that the same subproblems are solved multiple times, which can be optimized using dynamic programming. Memoization and tabulation, which are the two main techniques to store and reuse the results of subproblems. Finally, state definition, which involves identifying the variables that define the subproblems. Next, let's talk about subsequence problems. We need pattern recognition, which means understanding the underlying patterns and relationships within the sequences. State transitions, or defining how to move from one state to another. A bottom-up approach, meaning building up solutions from smaller subproblems. And finally, space optimization, which will help us to reduce memory usage. So what exactly is a subsequence? A subsequence is a sequence that can be derived from another sequence by deleting some or no elements without changing the order of the remaining elements. Let's dive into our first subsequence problem. The longest common subsequence, often abbreviated as LCS, is a classic dynamic programming problem. The longest common subsequence finds the longest subsequence common to two sequences. The subsequence must appear in the same relative order, but not necessarily contiguously. For example, if string 1 is A, B, C, D, F, and string 2 is A, X, C, Y, E, Z, then the longest common subsequence is A, C, E, which has a length of 3. The recurrence relation for LCS is the dynamic programming of I and j is equal to the longest common subsequence length of text1 from 0 to I-1 and text2 from 0 to j-1. If the character at text1 of I-1 is equivalent to the character at text2 of j-1, then the dynamic programming of I and j is equal to 1 plus the dynamic programming of I-1 and j-1. Otherwise, the dynamic programming of I and j is the maximum of the dynamic programming of I-1 and j, and the dynamic programming of I and j-1. The base cases are dynamic programming of 0 and j is equal to dynamic programming of I and 0 is equal to 0. The final result is the dynamic programming of m and n, where m and n are the string lengths. Here's the Python implementation of the longest common subsequence algorithm. First, we define a function called longest common subsequence that takes in two strings, text1 and text2. Then we get the lengths of the strings and store them into the variables m and n respectively. We initialize a dynamic programming table with zeros. This will be a two-dimensional array with m plus 1 rows and n plus 1 columns. Now we fill in the dynamic programming table. We iterate from 1 to m plus 1 and 1 to n plus 1. If the character at text1 of I-1 is equal to the character at text2 of j-1, then we assign the value at dynamic programming of I and j to be 1 plus dynamic programming of I-1 and j-1. Otherwise, the character at text1 of I-1 is not equal to the character at text2 of j-1. In this case, we assign dynamic programming of I and j to be the max of dynamic programming of I-1 and j, and dynamic programming of I and j-1. Finally, we return the value at dynamic programming of m and n. The time complexity of this algorithm is big O of m times n, where m and n are the lengths of the two input strings. The space complexity is also big O of m times n, because we are using a two-dimensional array to store the results of the subproblems. Next up is the longest increasing subsequence, often called LIS, which finds the longest subsequence where the elements are in ascending order. The longest increasing subsequence is the longest subsequence of a given sequence such that all elements of the subsequence are sorted in increasing order. For example, if the input array contains the values 10, 9, 2, 5, 3, 7, 101, and 18, then the longest increasing subsequence would be 2, 5, 7, and 101. This gives us a length of 4. The dynamic programming approach for solving this problem is, the dynamic programming of I is equal to the length of the longest increasing subsequence ending at index I. Initially, dynamic programming of I is set to 1 for all I. Then we can define the recurrence relation as follows. For I in the range of 1 to n and for j in the range of 0 to I, if number at I is greater than the number at j, then the dynamic programming of I is equal to the maximum of dynamic programming of I, and dynamic programming of j plus 1. The final result is the maximum of dynamic programming. Here's a Python implementation of the longest increasing subsequence algorithm. First, we define a function called longest increasing subsequence that takes in a list of numbers. If there are no numbers in the input, then we return 0. Otherwise, we get the length of the numbers list and store it into the variable n. Next, we initialize a dynamic programming array with ones. We do this because the minimum length of an increasing subsequence is 1. Then we fill in the dynamic programming array. For I in the range of 1 to n and j in the range of I, if number at I is greater than number at j, then we assign dynamic programming of I to be the max of dynamic programming of I, and dynamic programming of j plus 1. Finally, we return the maximum value in the dynamic programming array. This O of n squared algorithm can be optimized to O of n log n using a binary search approach with a patient sort-like technique. Let's explore the edit distance problem, also known as the Levenshtein distance algorithm. Edit distance measures the minimum number of operations required to transform one string into another. There are 3 main operations: insert, which means to add a character; delete, or remove a character; and replace, to change a character. As an example, the word intention can be transformed into the word execution with an edit distance of 5. The operations are delete I and insert e, delete n, delete t and insert x, replace e with c and insert u. The recurrence relation can be defined as the dynamic programming of I and j is equal to the edit distance between word 1 from 0 to I minus 1 and word 2 from 0 to j minus 1. If word 1 at I minus 1 is equal to word 2 at j minus 1, then the dynamic programming of I and j is equal to the dynamic programming of I minus 1 and j minus 1. Otherwise, the dynamic programming of I and j is equal to 1, plus the minimum of dynamic programming of I minus 1 and j, which represents the delete operation, dynamic programming of I and j minus 1, which represents the insert operation, and dynamic programming of I minus 1 and j minus 1, which represents the replace operation. The base cases are the dynamic programming of I and 0 is equal to I, and dynamic programming of 0 and j is equal to j. The final result is dynamic programming of m and n. Here's a Python implementation of the edit distance algorithm. We define a function called edit distance that takes in 2 strings, word 1 and word 2. Then we get the length of the strings and store them into the variables m and n, respectively. Next, we create a dynamic programming table of size m plus 1 by n plus 1. Next, we handle the base cases. For I in the range of m plus 1, we assign dynamic programming of I and 0 to be I. For j in the range of n plus 1, we assign dynamic programming of 0 and j to be j. Next, we fill in the dynamic programming table. For I in the range of 1 to m plus 1, and j in the range of 1 to n plus 1, if the character at word 1 of I minus 1 is equivalent to the character at word 2 of j minus 1, then we assign dynamic programming of I and j to be dynamic programming of I minus 1 and j minus 1. Otherwise, the character at word 1 of I minus 1 is not equal to the character at word 2 at j minus 1. In this case, we assign dynamic programming of I and j to be 1 plus the minimum of dynamic programming of I minus 1 and j, which represents a delete, dynamic programming of I and j minus 1, which represents an insert, and dynamic programming of I minus 1 and j minus 1, which represents a replace. Finally, we return the value at dynamic programming of m and n. Edit distance has many applications. These include spell checking, DNA sequence alignment, and plagiarism detection. Now let's look at the subset sum problem, which is a classic dynamic programming problem with binary decisions. The subset sum problem determines if there exists a subset of a given set with a sum equal to a given target sum. For example, if we're given the set 3, 34, 4, 12, 5, and 2, and we're also given the target sum of 9, the solution is true. The subset 3, 4, and 2 sums to 9. The dynamic programming approach that can be used to solve this is as follows. First, create a Boolean dynamic programming table with dimensions n plus 1 by sum plus 1, where n is the number of elements in the set. Dynamic programming of I and j represents can we make the sum j using the first I elements? For each element we have two choices: we can include it or exclude it. The base case, dynamic programming of 0 and 0 is set to true, as an empty subset sums to 0. Then we can apply the recurrence relation. Dynamic programming of I and j is equal to dynamic programming of I minus 1 and j, or dynamic programming of I minus 1 and j, minus the array at I minus 1. Dynamic programming of I minus 1 and j means that we exclude the current element. Dynamic programming of I minus 1 and j, minus the array at I minus 1, means that we include the current element. Here's a Python implementation of the subset sum problem. We define a function called subset sum that takes in an array and a target sum. Then we get the length of the array and store it into the variable n. Next, we create a dynamic programming table that is initialized to false. This table has the dimensions of n plus 1 by target sum plus 1. Next, we assign the base case. An empty subset can form sum 0. So for I in the range of n plus 1, we set dynamic programming of I and 0 to true. Next, we fill in the dynamic programming table. For I in the range of 1 to n plus 1, and j in the range of 1 to target sum plus 1, if the value at the array of I minus 1 is less than or equal to j, then we assign dynamic programming of I and j to be dynamic programming of I minus 1 and j, or dynamic programming of I minus 1, and j minus the array at I minus 1. Otherwise, if the array at I minus 1 is greater than j, then we assign dynamic programming of I and j to be dynamic programming of I minus 1 and j. Finally, we return the value at dynamic programming of n and target sum. The time and space complexity of this algorithm is big O of n times sum. Let's discuss some space optimization techniques to improve the memory efficiency in dynamic programming solutions. The first technique is one-dimensional array optimization. Many two-dimensional dynamic programming problems can be optimized to use only a 1D array, if each state depends only on the previous row. Instead of dynamic programming of I and j, we can simply use dynamic programming. For I in the range of 1 to m plus 1, and for j in the range of n to 0, we can update dynamic programming of j. The next technique is a rolling array technique. When only the last few rows are needed, we can use a rolling array approach with modulo arithmetic. Instead of m rows, use only 2. We can define a dynamic programming table of size 2 by n plus 1. Then for I in the range of 1 to m plus 1, and j in the range of 1 to n plus 1, dynamic programming of I mod 2 and j can be set to some calculation. Another technique is state compression. For Boolean states or small integer values, we can use bit manipulation to compress the state representation. We can use bits to represent states. For I in the range of n, if some condition, then state or equals 1 left shifted by I bits. We can also check a bit by using if state and 1 left shifted by j bits. Finally, there is sparse table optimization. When the state space is large but sparse, most cells are unused. We can use hash tables instead of arrays. Instead of a full 2D array, we can use a dictionary or hash map. For state invalid states, we can set key to be I and j, which represents the state, and then we can set dynamic programming of key to some value. Let's make a comparison and summary of the algorithms that we've discussed. First, we'll talk about the longest common subsequence. This is a string matching algorithm with a time complexity of big O of m times n, and a space complexity of big O of m times n, where m and n are the lengths of the input strings. The key characteristic is character-by-character matching. Next, the longest increasing subsequence. This is an array sequence algorithm with a time complexity of big O of n squared, or big O of n log n if optimized, and a space complexity of big O of n. The key characteristic is that it has strictly increasing values. Next, edit distance. This is a string transformation algorithm with a time complexity of big O of m times n, and a space complexity of big O of m times n, where m and n are the lengths of the input strings. The key characteristic is that it calculates the minimum number of operations to transform from one string to another. Finally, there is the subset sum algorithm. This is a number combination algorithm with a time complexity of big O of n times sum, and a space complexity of big O of n times sum, where n is the number of values in the set, and sum is the target sum. The key characteristic is that there is a binary decision for each element in the input set, that is, to include it or to exclude it from the sum. Key takeaways. All subsequence problems use overlapping subproblems and optimal substructure properties. State definition is crucial for successful implementation. Most solutions can be optimized for better space complexity. Memoization or the top-down approach and tabulation or the bottom-up approach are both valid approaches. Many subsequence problems can be solved using similar dynamic programming patterns. And recognizing when to use 1D versus 2D state representation is important. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.